go ahead and do an example. Example 2. Okay. A temperature distribution, so now we can actually use a nice physical situation. A temperature distribution in space is given by the formula. It's given by the, let's just not use the word formula, is given by the function temperature xy equals 12 plus 4 cosine x cosine y plus 9 cosine 2x. Let me actually change this to, no, that's fine. Okay. So a temperature distribution in space is given by the function, this thing right here. All that means is that wherever I am in terms of x and y, and notice this is a temperature distribution in space, the z can be any value, so the z doesn't change. So what we're looking at is just some sort of a cylinder, so z is infinite values. We're still talking about 3 space, but notice we've used 2 variables. So it's x and y that's changing here. Now, so at a given point xy, the temperature at that point is going to be T of xy. That's what this means, a temperature distribution. At different points in space, you're going to have different temperatures. All right. Now, at the point, here's our problem. At the point pi over 3, find the direction of the greatest increase in the temperature. In other words, once I get to the point pi over 3, and if I want to move in the direction that gives me the highest and fastest increase of the temperature, what direction do I move in? Well, I already know the answer to that. The direction of maximal increase is the direction of the gradient vector. That's what's nice. So all I have to do is I have to find the gradient vector. Nice and easy. Okay, so now let's go ahead and find the gradient of t. That is going to equal, and I hope that you will confirm this for me. I'm just going to write this out. It's going to be minus 4 sine x cosine y minus 18 sine 2x, and the y-coordinate is going to be minus 4 cosine x sine y. Okay, looks complicated? It's not. It's just functions. That's it. We're going to be sticking numbers in here. Pi over 3, it's a 60-degree angle. We already know what all these numbers are. Okay, so now let's go ahead and evaluate this at the point pi over 3. So the gradient of t at pi over 3 is going to equal, and I am going to write all of these out actually, minus 4 times rad 3 over 2, and again, I'm hoping that you will confirm my arithmetic here, minus 18 times rad 3 over 2, and then this one is going to be minus 4 times 1/2 times rad 3 over 2. And again, arithmetic is just arithmetic. It's not as important as the mathematics. That's what's important. There will always be somebody there to check your arithmetic. There won't always be somebody there to check your mathematics, the concept. Okay, that's going to equal negative rad 3 minus 9 rad 3, and then negative rad 3. And I'm actually going to go on to the next page here because everything's lines here. So our final answer is minus 10 rad 3 minus rad 3. That's it, this vector. If I move in the direction of the vector minus 10 rad 3 minus rad 3, from pi over 3 at that point, that's the direction that's going to give me the maximal increase in the temperature, the gradient vector, the direction of the gradient vector. Okay, so let's go ahead and write at pi over 3, pi over 3, the gradient, not the gradient, the greatest increase in t happens when we move in this direction. When we move in this direction. Now, the rate of this change, the rate of this increase, the rate of this increase is just the norm of that vector. Of this increase is the norm of the gradient of t at pi over 3, pi over 3. And that's equal to radical 303. That's it. So as I move in the direction of the gradient, the temperature is going to be changing by that much for every unit change in that direction. So that's it. That is the directional derivative, and that is the geometric interpretation of the gradient. Thank you so much for joining us here at Educator.com. We'll see you next time. Bye-bye.